Small block. He has an old 76 PW in that. So it's his overboard and stroke to 2276. So that's it. It's not quite as big as you can know. You can actually go to 2430 or something. It's the biggest you can get on an old Volkswagen engine. 1600 stroke. His is straight.
Good, Paul. How are you?
How are you?
Pretty good.
Where did you find that S2 video?
Somebody passed it to me.
That's super cool.
Yeah. It showed a brief picture of the landing gear system, or at least components. The down or the safety lock that they use for the nose gear, it's a C clamp, and that's what they use. And for the main gear, it's a collar that goes around a portion of the actuator to hold it in the lock position.
That's interesting.
We don't have the main gear down lock or the ground lock anyway, but we've got on the mock-up anyway. If you look on the nose gear, there's a little plaque and we're a little placard area, and what's hanging there is in fact for the ground lock for the nose gear. It's a C clamp. It goes around the over center. Yeah,
That's interesting. I guess it works.
it works.
Yeah. Is it painted red?
The streamer was. Somebody liked the streamer enough to take it. Okay, let's talk a little bit more about troubleshooting. First thing is no pressure in a hydraulic system. And I think we talked about this earlier. A lot of people will jump to conclusions. They'll think that the problem is the pump. It's not, in most cases anyway. The pump is really only a device that pushes fluid. But if there's fluid returning back to the reservoir, the pump is really doing the job that it's supposed to do. So what creates pressure? Well, what creates pressure is confinement of hydraulic fluid. If you're not confining the fluid, you'll never be able to build pressure. So maybe you've got an open relief valve, or you've got some hydraulic component that is bleeding fluid back to the reservoir or overboard, and you're not able to develop pressure. That's probably the reason. So remember, pressure isn't created by the pump. The pump is just a means to an end. Another thing, with systems having gauge mounted on the gas side of the accumulator, the gauge will actually tell you two things, just like a system pressure gauge will. If a gauge is mounted on the gas side of the accumulator, when there's no system pressure, which you should be indicating is just the gas pressure in the accumulator. However, if that gauge, or if the system is under system pressure, you develop fluid flow and confining the fluid, whatever pressure you have above that gas charge will be indicated on the gauge. So you can use that for checking the pre-charge in the accumulator. You can also use it for verifying system pressure, and maybe compare it with a cockpit-mounted gauge in order to figure out if you've got correct pressure. Remember too, just as I've mentioned this a couple of times, if you've got aircraft instrumentation, we're going to be using that first for indication of trouble. Sometimes if you're substituting separate instrumentation or sources of power, you're bypassing portions of the circuit that may have a problem. So you can verify one gauge against another. That's one thing. If there's a restriction of the pump outlet in the system pressure regulator, the system pressure will drop. This is kind of a strange thing that happens with a lot of hydraulic systems. The gauge responds, of course, to system pressure, but it also responds to flow in a way. So it says when some unit is actuated, and maybe there's a blockage or a kink in the line, the system pressure gauge will initially indicate a drop in pressure. So it says, if there's a restriction of the pump outlet or between the pump outlet and the system pressure regulator, the system pressure will drop gauge reading when some unit is actuated. The pump is unable to provide the volume of fluid that the system requires. So sometimes, again, it isn't just pressure that it's indicating, it's really indicate a restriction that might be in the circuit. Anything else? System pressure is higher than normal. You all know that in many hydraulic systems, we've got either an unloading valve or we've got a pump that contains a compensator. That's the controlling mechanism for system pressure. As a secondary device, you may also have a relief valve in the circuit as well. So pressure higher than normal, what I kind of suspect is the control, whatever is controlling system pressure has failed. If you've got an unloading valve and a relief valve, the pressure is higher than normal, the relief valve, system relief valve is controlling pressure. Knowing that, there is some indication also that the unloading valve may have failed. If the relief valve is buzzing or chattering, in some designs, what that means is that the relief valve is doing what it's supposed to do. It's buzzing and chattering, opening rapidly and closing rapidly to control system pressure. Additionally, a lot of relief valves will be warm as a result of doing that. If that goes on for a long period of time, what you might expect is that the hydraulic fluid will turn black. What happens is that the oil, the hydraulic fluid, begins to receive excessive heat, and it will begin to char or coat the fluid so that it discolors the fluid where it becomes really black. But it takes quite a bit of time for that to happen. Initially, what you might notice is that the relief valve is just chattering and buzzing. Also, it says with an open relief valve, it will cause a variable displacement pump to overheat as the pump continuously is delivering full flow in an attempt to build system pressure. So if the relief valve is wide open in that circuit, that means that the pump senses that as a low pressure condition, and it does what it's supposed to do. It tries to build system pressure by allowing full flow into the circuit. The pump eventually is going to overheat as a result of that. So that's just the nature of the beast. Lower than normal system pressure could be caused by anything that provides a return path back to the reservoir where you shouldn't have one. So you've got an internal leak. If you have an external leak, well, that is what it is. But if you can't trap or confine hydraulic fluid, you can't build pressure. It might be due to a relief valve that is stuck open. Maybe there's some debris in it that prevents the valve from closing and being seated. It might be that the pressure regulator or unloading valve is stuck in the bypass position, or the compensator is stuck maybe in zero flow. So, okay. Loud hammering noise might indicate a problem with the accumulator. The accumulator serves several functions in a hydraulic circuit. There's about 6 or 7 different things that an accumulator can do. No one particular function is more important than any other. However, you hear a hammering in the line. One function of an accumulator is to stabilize the hydraulic pressure. And if you open and close selector valves, there's no counterbalance force, or at least device that will absorb the shock of shutting a valve off. So the accumulator is working like a condenser or a capacitor in an electrical circuit. It absorbs hydraulic pressure, or at least surges anyway. So might be the gas charge in the accumulator is gone. Again, we can look at system pressure gauge for building or releasing pressure, and some systems again have a gauge on the gas side of the accumulator. And that's really handy. Some of the earliest of the Boeing aircraft, the 700 series aircraft, their system pressure gauge that was mounted in the cockpit was really a gauge that was tied to the gas side of the accumulator. And the gauge, and if it was functioning normally, would never indicate 0. What the gauge would indicate would be the pre-charge pressure. And then when system pressure was built above it, the gauge, of course, would then, in fact, read system pressure. That's been changed now, but in the early days of Boeing aircraft, that's what they did. It says when normal system pressure suddenly drops to 0 as the pump stops, the accumulator may have lost the gas charge. Verify the proper pre-charge pressure and check for a leaking service valve. We can check for a leaking service valve easily. If you're looking for a leak of the service valve, soapy water will do the trick. If you see bubbles coming from the service valve, Usually that indicates that the gas charge is leaking out of it. Might be the gasket on the service valve, might be the valve itself, or might be not torqued correctly, but it's leaking gas. The accumulator serves a function of supplementing the pump under peak load. So again, if there's no stable or at least additional pressure after the pump is cut off, it may be that again that the gas charge has been removed or at least lost out of the accumulator. Regulator chatter caused by low reservoir level. What's happening is the symptom is going to be present in the regulator, but the problem might be something else. In this case, insufficient gas charge in the accumulator. This is a good a lesson maybe to remember. Sometimes a symptom will develop someplace in the circuit, but the problem is really another component. So in this case, the regulator chatter, what I kind of suspect is the regulator is cycling too frequently, and what might be causing that again is the inability of the accumulator to hold the unloading valve in the kicked out position. It's transitioning back to kick in too suddenly, so that'll cause chatter. Actually, a better thing that might define what's happening is you're not, the cycle time is actually too short. You're going from kick out back to kick in too short of a period. This also leads me to kind of know and understand what normal is. It's possible that maybe a certain period of time has got to elapse before the unloading valve kicks back in again. But again, you won't know that until you figure out what actually normal is in the circuit. Broken or missing pilot valve spring in an unloading valve. Well, to cut right to the chase, the unloading valve goes right to bypass. The spool, the pilot valve, and all of those unloading valves will float to the upward position, which now triggers the unloading valve to bypass fluid back to the reservoir. There's no force to hold the pilot valve down, so the unloading valve responds by just dumping all of the system pressure through the bypass spool. Leaky regulator check valve usually causes early kick in. I think we've talked about this too when we discussed unloading valves. If you're unable to hold pressure in the accumulator, what might be the reason is that the unloading valve, the check valve in the unloading valve has got a burr in it. What you're doing is you're draining the pressure out of the accumulator, and then the unloading valve sees that as a drop in pressure, and of course responds by now cycling the unloading valve to the kicked in position, but it's doing it earlier than it should. There's another problem as well, and it would be late kick out. Late kick out is usually caused by a burr or an obstruction that holds the bypass spool open. When you're building up pressure, all of the fluid flow should be going into the accumulator from the pump. But if some of the fluid is bypassing it, the unloading valve and going back to the reservoir, it's going to take a longer period of time for you to eventually get kicked out. So that's why they call it late kick out. So you might want to remember that. Failure of a variable displacement pump compensator might be noted by loss of pressure or abnormally high pressure, depending upon the mode of failure. And it says, note, normal pressure differential between full flow and zero flow is frequently only 50 psi. This makes it really difficult to troubleshoot systems that have got variable displacement pumps. Many of those pumps will push out the maximum fluid flow. They'll be in the full flow position for the bulk of their operating period of time. Only when the last 50 psi necessary to go to zero flow is attained does the compensator finally shift to zero flow, and then there's all of the flow from the pump is diverted back to the reservoir. It's not like an unloading valve. An unloading valve has got a definite period for kick in and kick out. The pump that has a compensator, it just delivers enough flow that's sensed by the needs of the system. So it's very much difficult to be able to troubleshoot something like that. Oh, by the way, too, if you have to adjust a variable displacement pump, would that pump be adjusted for developing pressure and flow in the zero flow position or in the full flow position? What do you think? How would you be able to adjust pressure? How would you have to be able to do something like that? You'd have to block the flow coming from the pump and then make an adjustment on the compensator. If you block the flow from the pump, that forces the pump to go to the zero, it goes to zero flow. So then and only then can you really adjust the compensator in order to provide for system pressure. So if you have to adjust a variable displacement pump that has a compensator in it, it's adjusted in really technically the zero flow condition. You have cut off the flow, the discharge of the pump, and then and only then can you really adjust the compensator. When the pump is in the full flow position, you really don't have any, you have no sensation of what the system pressure is. So what you have to do is you have to block the flow from the pump in order to be able to regulate, or at least set the compensator in it. So it's got to be in the zero flow position. Pump chattering, subsequent overheating might indicate that air is at the inlet of the pump. Causes might include a low reservoir level, a leak in the line between the reservoir and the pump. The chattering, I guess, is really a more severe condition of kind of cavitation in the pump, but nevertheless, it'll cause it to sometimes chatter. Okay. Slow actuation of a unit, slow moving. And again, how slow? Well, again, you have to know what normal is. What I would kind of suspect is internal leakage. It might not even be in the actuator itself. Whatever fluid flow is being delivered to it, maybe the volume has been reduced or restricted in some way. Might be a leak between the chambers in the cylinder in the piston, so that might cause it. It says this leakage may also cause the regulator to cycle more frequently than usual. Electrically driven pump systems may show an excessive ammeter load. This is interesting too. When you look at a lot of landing gear systems that are purely electric in operation, one method to kind of determine whether or not the system is working correctly is the amount of amperage being drawn when the gear is extended and retracted. It indicates sometimes a malfunction or at least a rigging problem where there's an excessive amount of friction. So that's indicated because the motor will draw more load, and what you might find is that the ammeter that's in the aircraft, if they have one, or if you have an auxiliary ammeter that you have to measure current, will indicate more of a load. The motor is loaded for an abnormally long time. The leaking component may produce hot spots and become abnormally warm. This is true a lot of times with pumps where you've got an excessive amount of clearance in pumps. The stagnant fluid that's not able to be exchanged into the circuit or back to the reservoir causes the pump to overheat. So sometimes a lot of pumps that are excessively warm will become a little bit warmer than normal. Spongy actuation, you've got give on an actuator when you push on it, well, or just like with brakes where we've got a brake actuator, that usually indicates air in the circuit. And the air is compressible along with other gases. And again, spongy actuation is usually the cause is going to be air that's trapped in the circuit. Most hydraulic circuits are self-bleeding because they have the ability to pass the fluid back to the reservoir when the circuit is in operation. However, not all of them work really well. A lot of brake systems, in particular for independent brakes, they require separate bleeding in order to get air out if it's in fact is trapped in the circuit. But with many hydraulic systems, they're self-bleeding. It says, if a component has been replaced, it should be cycled a number of times to purge air back to the reservoir. If the actuating time decreases each time the system is cycled, the air is being worked out of the fluid. Some systems do not purge air normally. Special instructions are usually supplied by the airframe manufacturer to remove trapped air. Regulating and relief valves are adjusted in a specific order. In lieu of any specific airframe information, there's a hierarchy of adjustment. We always adjust from the highest pressure down to the lowest pressure in that particular order. So for example, if a system has a thermal relief valve, those are usually tied to actuators, and those will have to be adjusted first. You may have to use jumpers or caps or plugs in order to prevent other components or at least other regulating devices from actuating before you can verify and possibly adjust the thermal relief valve. Once that's been adjusted, then you can adjust usually the system relief valve, but again, you're going to have to sometimes jumper or block the actuation or the operation of the unloading valve why you do that. And this isn't as difficult as you might think. You don't have to use an engine-driven pump in order to get the flow. You can use a hand pump in order to be able to adjust pressure. You just have to block the other components that are in the circuit that might control it before the particular device you're trying to set is reached. Okay. Anything else? I think that's about it. Sometimes a hydraulic gauge, if the gauge fluctuates rapidly and the pointer is forming a blur, an indication that there's air in the line. Many times the snubber alone isn't sufficient in order to do it. Years ago, we had the mock-up board that we have out in the shop required replacement of the bladder and the accumulator. And the problem that I noticed was that the gauge, the system pressure gauge, the needle would tend to just mysteriously increase in pressure over a period of time, even after you stopped using the hand pump. The problem was the bladder that was in the accumulator had developed a leak. The gas pressure, the nitrogen, was able to find its way into the fluid. Ultimately, the gas found its way to the bourdon tube of the gauge, and it caused the gauge to indicate an increase in pressure. As that volume of gas reached the bourdon tube, it began to expand, and of course, it causes the bourdon tube to go erect, and made the needle sweep upstream or up. So that was the cause. So again, kind of strange, but that's the way that it worked. Open center hydraulic systems, the big thing to remember with those, you only build pressure when you divert the fluid to a component. Otherwise, the nominal pressure in many of those systems is only about 50 psi, just from fluid friction that's passing in the line. So with the selector valves in the open position, it means that hydraulic fluid is just circulating back to the pump with minimal pressure being developed. Sometimes it's not even enough to register on a system pressure gauge, so, but very low. Only when you operate a component by turning a selector valve to a position where to operate an actuator is pressure actually developed. A simple schematic for operation of hydraulics. This is in the fluid powered book, and I think it's on page 255. And it covers the operation of a brake system for both normal brakes and what they consider to be reserve brakes. And we'll talk about this, I think, next week, but in any event, you might, we'll take a look at this particular slide for its operation. They don't really, your textbook is so old, you can see some of the numbers that they're talking about with the solenoid selector valve for the hydraulic fluid. They've been washed out of the illustration, you can't actually see it. But this is the port number 1, port number 2, and port number 3, and we'll talk about this a little later. Remember what solenoid selector valves do. They allow you to route hydraulic fluid, but rather than using a manual control, it provides for automatic control by electromagnetism. So when we develop current in the coil, what it does is it causes a rerouting of hydraulic fluid to a particular point. With no electrical power applied, the solenoid selector stays in whatever position that it was last commanded in, and that's where it stays there. It says this: the solenoid selector valve de-energized fluid enters from port 2 and exhausts out of port 3. So what happens is the fluid comes into this port from 2 to 3, as long as the solenoid hasn't been actuated. And it says the solenoid selector valve is with an energized fluid enters through port 2 and it's exhausted out port 1. So when we provide electrical power to the coil of the solenoid valve, it pulls this down so the fluid flow goes from port number 2 through port number 1. We'll talk about this maybe a little bit more in detail next week. The controlling circuit is just an electrical switch. It's a 3-position switch. One of the positions is auto, the other position is off, and the other one is a momentary contact for reserve brake. But we'll talk about this next week. Okay. Next up, in addition to the exam next week, I think you've got a couple of written assignments that are due, are you not? Mm-hmm. Okay, let's take a look at that and see what we got. Let's see. This is for the lecture. Let me see what we have. Due on 5/9, research and construct a 3-page minimum written report detailing an aircraft accident where hydraulic malfunction was a cause or a major contributing factor to the accident. Cause, investigation, and outcome information are required. College level assignment and will be graded as such, due 5/17. Did I send, I think I did, I sent you out a list of aircraft not to report on?
Yeah.
Okay, observe that, please, okay? And let's see what else we also got. For the lab, if you're in the lab, we have something else too. Let's see, spring. This will work. This is the fall, isn't it? Yeah. Okay. Let's see what it's got for the fall. Design, illustrate, describe your own hydraulic system. Design the system using concepts gained from the study of systems discussed in class and examples from your textbook. Illustrate the system using industry standard ISO hydraulic symbols. Did I send you some links for hydraulic symbols?
Yes.
Okay. I think I also sent you a couple of videos too to watch as well. So hopefully you can get an idea of how they use those symbols to complete a hydraulic circuit. Describe the operation of the system in detail. So you're going to have to illustrate it, you're going to have to describe it, and design, illustrate, and describe. Question?
Yeah, is it like a minimum amount of like components you want in this hydraulic system to make it worthwhile?
Yeah, basic of maybe 5 or 6 components earns you a 70. How's that?
So 70 would give you an A and 5 would give you
Yeah, you know, you get 70 with 5 components. If I want to put in one more, maybe 72, another one, 73. But what I'm trying to have you do is design your own system. Please don't copy something out of a book and submit it as yours. I view that as plagiarism. So I don't care if your circuit operates I don't know, a lid for a toilet. I don't care.
That's good.
However, it's going to be your own circuit. If you want to make a can tap or something else for, home use, whatever you want to do is fine by me. But again, don't copy something out of a book and submit it as your own. Okay? You'll have to use the ISO symbols as well. Don't submit a pictorial. So don't waste time trying to draw a unloading valve or a pump or anything like that. You're using the simplified version of the ISO symbols in order to be able to do it. Okay? All right.
Can this all be just handwritten?
The illustration, it can be, but any text, anything that has to be done in text, just word process it.
As far
So-
as description?
Yeah, description, just word process. There's reason to my madness. You may say, why is he asking me to do something like this? When I started work at Sikorsky, I worked as a tech writer, and I gained a whole lot from being able to describe things in detail. I think that was probably one of the most important skills that I learned on the job there. So also being able to logically construct something from a knowledge base of whatever I had studied in the past. In this case, it's hydraulics. You're going to kind of have to do the same thing. So that's the reason that I want to do it. All right. Any questions? Anything at all? Okay. For resources too, for troubleshooting, what I have for you. Let's take a look here. I want to take a look in the Aviation library. I've got a few things that might be of value to you. What's the login again? Repair with Pride, right?
Yeah.
Okay. Let's take a look in their film articles. Ooh, this is good. Peculiar to Eaton projects, or products anyway, but you might want to take a look at this. But it's in the Aviation library under airframe articles, and we've got a pretty good troubleshooting guide here in maintenance tips section, in addition to some standards that they use for hydraulics. It gives you general information on contamination control, hydraulic hints, a little bit on recommendations for hydraulic systems for engineers, pipe sizes for engineering, definitions and functions of what things do, again, some ISO symbols that are here, and maybe even some information on formulas that are used. Also, I've got another thing from Vickers, Eaton Vickers anyway, on troubleshooting, another document, but fairly comprehensive as well. And again, generic enough, I think that it might be of value if you have to do a little bit of troubleshooting. It just not the specific to Eaton products, but a lot of troubleshooting trees in here to kind of look at. And for some of their pumps anyway, so quite a bit there. And I think I got another one here somewhere. Here's one from Ultra Metal Manufacturing, not too bad. It's not very long, but it gives you a little bit of things to kind of look at. Okay. Oh, and there's one other piece of literature you might want to look at too. There's something in here that might be worthwhile putting here in your own flash drive. If I can find it here. This one. All sorts of information in simplified version for design of hydraulic systems. Lots of info. Pumps, actuators. One of my former students was kind enough to give this to me. I think he paid for it. He paid a pretty penny, but it's actually pretty good. Anyway, some things to kind of look at. All right. Let's see, what else do I want to do? Let's take a look here.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Hello, this is Carl from lunchboxsessions.com, and in this video we're going to have a look at the flow paths that may exist within a hydraulic system or that may come to exist in a hydraulic system if there was a fault, and how reading the system pressure gauge and understanding the various expected pressure drops along various paths within the system can help you diagnose faults. And so two earlier videos that we produced, one by the title Pressure Drops in Series Circuits, and another one by the title Pressure in Parallel Circuits, may be very helpful videos to review before watching this one, because in this video we're dealing with a hydraulic system that has both series and parallel circuits. And of course, once again, we've got our generic resistances called spring-loaded check valves. And our spring-loaded check valves have various different spring tensions listed by their equivalent PSI value. And we've got a couple of shutoff valves as well. In fact, just take a moment to analyze the system as you see it here and go ahead and predict yourself what you expect to see on the system pressure gauge once I turn on the pump. Let me just add a qualifier here that all of these dark blue hydraulic lines, anywhere where you see them other than inside the check valves themselves, any of the main blue hydraulic lines out in the open here, all of these are sized large enough to take the entire flow from our pump on any one particular line, meaning that the hoses or lines pose no resistance in this ideal model. The only resistances that we have are the spring-loaded check valves themselves. Go ahead and predict what you expect to see on the system pressure gauge once I turn on the pump. Are you ready? Let's see what happens. Aha! We've got 200 psi system pressure reading. Did you guess correctly that the flow path would be through this 100 psi spring-loaded check valve at the top? Of course, it had to be. That is a mandatory flow path given how the circuit is laid out. But then, given the qualifier I gave you about the line sizes, did you guess correctly that all flow would pass next through this lower branch? And so, as you know from earlier videos, that the system pressure reflects the easiest path that the pump's flow could take. We've got 100 psi on the first spring-loaded check valve, and another 100 psi spring-loaded check valve downstream. So those two loads add together to give us our system pressure. I'm going to turn the pump off. And now I'm going to close this shutoff valve to make it a path of very, very high resistance. So take a moment to have a look at this circuit. Where do we expect our next flow path to be? And go ahead and estimate what you believe the system pressure will be when I turn the pump back on. Here we go. Aha, 500 psi. Congratulations to you if you got that right. Our new path of least resistance, given the closed shutoff valve, is through the 100 psi check valve, then this 300, then this 100. We add those three resistances together to find out that our system pressure is expected at 500 psi. All right, you're getting the hang of it. Let's turn the pump off one more time, and let's close this shutoff valve over here on the far right. And of course, we've only got one main flow path available to us now. We don't have any parallel branches available. So hopefully everyone gets this right. And here we go. We have a 600 psi system pressure. So in your hydraulic system, if you were expecting 200 psi when you turned the system on, and yet you got 600 psi system resistance, that would be a pretty easy way to understand that flow is not occurring in this branch. If you were expecting it to occur in this branch, then you've got some information that you can use. Something is now indicating that there must be blockage or very high resistance to flow in this particular parallel branch. And if you knew what all of the rest of your expected pressure drops add up to, you would know that since you're receiving a 600 psi system pressure value on the system gauge, that the only branch where flow is occurring at this moment must be along this top branch here. And of course, you can't see inside hydraulic systems as you can on these animated models. So gathering up information about normal expected pressures for your hydraulic system really helps you when it comes time to troubleshoot. I'm going to remove a branch, and let's say we're working with a slightly simpler hydraulic system for a moment, where we've really only got two parallel branches that could open up. And if we knew in advance that this first load is a 100 psi pressure load on the system, a resistance of 100 psi, it could be a full flow filter, let's say, in front of a servo valve, perhaps. And perhaps further on down the system, we've got a hydraulic motor that is turning a screw conveyor or some other type of rotary device like a winch. And so if we know that, when that system is running, that hydraulic motor is running, that it is normally a 300 psi pressure drop. And this perhaps could be our return line filter, 100 psi on our way back to tank. So on a day when we don't get the 500 psi system pressure that we're expecting, and instead we get the 600 that you see now, that might be an indication to us that flow is blocked, passing through this last load on its way back to tank. Or that if it is a filter, has become so plugged that it's much easier for fluid to pass through the 200 psi check valve on this upper branch. So that's just one very simple way for us to understand how to use system pressure if we know what the normal expected loads are throughout the system and how they add up. They all add up to give us our system pressure. We know that we should have been seeing 500 psi on this gauge, and that when we don't see it, something's not normal. Okay, that's it for this go around. That's a simple tutorial. I hope that's been helpful. Thanks for watching.
We have hundreds of interactive resources like this live schematic.
Hydraulic systems have a lot of parallels with electrical circuits. With electrical circuits, you have loads in series and parallel. And with the pressure drops that you would expect in a hydraulic circuit and a series circuit electrically, that works the same way. If you sum all of the individual voltage drops in an electrical circuit that are in series, it should indicate the source voltage. In the case of a hydraulic circuit, it works the same way. So. Well, something to think, they briefly talked about it as well. A filter can exhibit enough back pressure to cause a substantial pressure drop, or at least a difference in pressure that you didn't normally anticipate. So there's always going to be some pressure drop that a filter in the return manifold is going to provide. But if the filter is blocked, or the element is blocked in some way, maybe from dirt, it causes a corresponding a higher drop in pressure that's indicated. Let's take a chance. Let's look at this. I haven't seen this yet, but sometimes they're valuable.
Literally pay for themselves the very first time they are used. The first tool is a good pressure test kit. The kit should include at a minimum one low pressure and one high pressure gauge. By low pressure we mean 0 to 1,000 psi, and by high pressure we mean 0 to 3,000. Of course, some systems will operate at a high enough pressure to need a 0 to 6,000 psi gauge. Small hoses and fittings should be included so that the gauges can be mounted wherever they're needed. Remember that the pressure gauge for a hydraulic technician is comparable to a voltmeter for an electrician or ENI tech, and most systems have only one gauge at the power supply. This is fine for measuring system pressure, but it can't tell us anything about pressures in any of the lines downstream. Paper mills in particular usually have test ports already mounted in the manifolds so that the technician can insert the portable gauge at various points to measure pressure and quickly track down a pressure loss. We may also need to know the pressure at some point in the hydraulic plumbing that is not in the valve manifold. That's no problem. There are pressure test ports available that can be mounted in any hose, pipe, or tubing, so that pressure can be read immediately whenever it would be valuable for troubleshooting. These gauges, fittings, and test ports are quite inexpensive, but they are invaluable to the hydraulic troubleshooter. They can also be used to take oil samples or release pressure in a hydraulic line to make the system safe to perform maintenance and repair. Another quite valuable tool is a flow meter. This tool is never used to its full potential, but to have it installed is almost like having X-ray eyes like Superman. We can't see through walls, hydraulic lines, or manifolds, but we can measure the flow traveling through them with a flow meter, which makes this tool the next best thing. And most people seem to think that a flow meter is unnecessary if there is a pressure gauge. We believe that this is the result of a failure to fully understand the difference between pressure and flow. Pumps are often replaced because the pressure is low. This is usually a mistake since the pump does not pump pressure. The pump delivers a rate of flow. This flow is met by a resistance and hopefully overcomes it. The result of this is pressure. In the schematic, the hand valve is shown fully open, allowing flow to be delivered to the drum. There's no significant resistance, so the gauge reads 0 psi. In this figure, the hand valve is closed. The pressure then builds until it overcomes the resistance of the relief valve spring, which is set at 500 psi. The gauge now indicates 500 psi, and the pump flow returns straight to the relief valve. The gauge tells us the total resistance of the system, but cannot tell us how much flow is being delivered by the pump. A flow meter should be permanently installed in the case string of any variable displacement pump so that pump wear can be easily tracked. Case flow is the fluid that is bypassed across the very tight tolerances inside the pump. We recommend that the case flow be measured and recorded at least once per month, since ambient temperature will have an effect on the flow. The higher the fluid temperature, the lower its viscosity will be, and the more case flow will pass. The first year that the case drain is measured, it will be noted that case flow will increase with temperature. System pressure will also cause case flow to increase by an amount proportional to the pressure. So it would be wise to monitor each case drain monthly and record the minimum and the maximum flow through a complete machine cycle, thus giving us a benchmark of what is normal for August as well as what's normal for February and every other month. Most pump manufacturers include normal ranges for case flow in their documentation. In order to understand fully how case flow tells us if the pump is serviceable, we must first understand how the pump functions. The example we chose was a pressure compensating piston pump. While most mills have a wide variety of pumps, all paper mills use piston pumps. The piston pump has a barrel that is turned by a shaft. Pistons are mounted on the barrel, and as the barrel turns, the pistons are stroked by a cam or swash plate. In this first example, only one piston is shown to demonstrate how the piston is stroked. A spring holds the cam ring at its maximum angle so long as the system pressure is below the setting of the pump compensator, 1200 psi in this example. Once the pressure builds to the compensator setting, the compensator valve will shift to deliver flow to the destroking cylinder. This moves the swash plate to a reduced angle, which limits the stroke of the pistons and reduces the flow to only the amount needed to maintain the compensator setting at the pump outlet. When the flow is blocked, as would happen when all directional valves are closed and the system is in idle condition, the destroking cylinder moves the swash plate to the full vertical position. In this position, the pistons do not stroke at all, so the pump delivers no flow. System pressure is maintained at 1200 psi, and any drop in system pressure will cause the pump to stroke and keep the pressure up. As the pistons stroke, oil will bypass across the tight tolerances between the pistons and the barrel. This bypassed oil fills the pump case and returns the tank through the case drain. As the pump wears, case flow will increase. With a flow meter mounted permanently in the case drain, pump wear can be easily monitored. On the rare occasions we find flow meters mounted on equipment, the case drain is usually where we find it. While it can be quite valuable to monitor a pump's condition, it can only tell us how the pump wear compares to the previous times it was measured. If the pump's condition is unknown when the flow meter is first installed, the pump could still fail unexpectedly. A good rule of thumb is that a new pump will usually bypass 1 to 3% of its total flow, and it should usually be changed once the flow reaches 10%, but this is not a hard and fast rule. A flow meter in the pressure line can tell us immediately and conclusively whether a pump is good or bad. This method can be used on either fixed or variable displacement pumps. If a pressure compensating pump is being tested, the compensator should be turned fully clockwise to its highest setting. This will cause the pump to behave as a fixed displacement pump, constantly delivering its maximum flow. The pump flow should be deadheaded and forced across the system relief valve. Before starting the pump, turn the relief valve adjustment to a very low pressure, fully counterclockwise until no spring tension is felt. When the pump is turned on, it will deliver its flow across the relief valve at a very low pressure. Even a badly worn pump will deliver all or nearly all of its flow when it's met with no resistance. Begin increasing the pressure on the relief valve and watch the flow meter. If the flow is maintained when the pressure is increased to normal system operating pressure, the pump is good and need not be replaced. If, however, the flow drops significantly as the pressure is increased, the pump is badly worn and has to be replaced. There are numerous other components that can be diagnosed with the flow meter. Any actuator that is moving more slowly than it should is either badly worn or not having the required amount of flow delivered. A flow meter can tell immediately which is the problem, but most plants would consider flow meters in every hydraulic line a bit excessive, and I would have to agree. If the tool budget allows, a portable non-invasive flow meter can be used to measure the flow rate of any hydraulic line, whether it's a metal pipe or a hose. These are quite expensive for hydraulic systems, but would not have to save very many hours of downtime to justify the cost. If it's decided to take the leap of expense, be sure that the one you purchase is intended for industrial hydraulic circuits. Since most of them measure the velocity of particulates in the liquid, the less expensive models will not work on industrial systems because hydraulic oil must be kept too clean for the particulate matter to be detected. Thermal imaging infrared cameras have dropped significantly in price in the last few years. They're worth their weight in gold, however, for finding temperature gains. They're more accurate and much easier to use than laser temperature guns. And certain temperature gains, such as inside of a manifold, are difficult, if not impossible, to confirm without the infrared camera. The first indication of impending failure of any hydraulic component is an increase in heat. This is because, by and large, when a hydraulic component fails, it leaks. Sometimes it leaks out on the floor, and the problem is obvious, but most of the time, the leakage is internal, which we call bypassing. Bypassing is always accompanied by a pressure drop. Any pressure drop that does no useful work generates heat because the energy intended to move a load is released locally. The manifold pictured has an unloading valve mounted on the top. The particular circuit was losing pressure when the pump should have been loaded. Clearly, in the infrared photo, heat is being generated at the valve. A voltage detector can show instantly if a solenoid is being energized. When the directional valve will not shift, we must first determine if electrical power is being delivered to the solenoid. The voltage detector will light up when the voltage is set. Another option is to use a steel ruler. Whenever a solenoid is energized, if it's functioning properly, a magnetic field will be generated. The ruler will be attracted to the solenoid. If no magnetic field is present, either the solenoid is not being energized or the coil is burned out. It's not at all uncommon for a lot of troubleshooting time to be spent on servo or proportional valves trying to determine whether there is an electrical or a hydraulic problem. Often the symptoms will be identical. The fastest way to tell is to isolate the valve from its electrical control and drive it from an outside source to see if the valve function changes. Any company that manufactures servo or proportional valves will also make test boxes for them. The box shown is a universal box with a connector terminal at the front. If you have a number of valves that use the same amplifier card, a brand-specific box will usually have a slot that plugs directly to the card. The servo analyzer isolates the servo both electrically and hydraulically to determine this condition. There are also portable analyzers, often called battery boxes or diddle boxes, for diagnosing valves without removing them from the system.
This guy's okay.
us a hand and talk about hydraulics. So we've got a few different things that we're going to discuss with this system here. This is a really nice hydraulic training unit that shows you all of the fundamentals on a hydraulic system. And Paul is going to go over this. So, by the way, I wanted to point out that Paul has been designing hydraulic systems for a very long time. He has a lot of experience in them, and also with troubleshooting and preventative maintenance and that kinds of things. So, we've got a number of things over here on another table that you can't see yet. That some other components and parts that we will get to later, and zoom the camera in over there so you can see all of that. And I've got some things here. It's going to be 4 sessions, and your first session is going to be components of the hydraulic system and fundamental elements that govern all hydraulics. Okay. Your second session is going to be component operations and how they fail. Third session is going to be inspection and troubleshooting. And the fourth session is going to be how to prevent the most common hydraulic accidents. So we are going to let Paul step in here and go over all of these subjects here. And I hope that this helps educate people on a hydraulic system. And not only the viewer that's watching this, myself included, I'm getting something out of this today. He showed me a few things on this, and it's really interesting to learn how these systems operate and the fundamentals of them. So we're going to go ahead and we're going to let Paul step in and start talking about the system components here. Okay, hope you guys enjoy.
Hi, this is Paul from the shop, and Adam's invited me by to talk a little bit about hydraulics today. And as you can see, we got a really nice hydraulic demonstrator here to be able to show you some things that people struggle with out in the field when they're trying to troubleshoot things like that on the hydraulic system. So what we'll do, I've broken this down into 4 different segments. The first segment is going to be components of a hydraulic system and some things that govern hydraulics, the fundamentals of all hydraulics like pressure and force and flow and speed and things like that. And the second section is going to be about component operation, how each one of these components operate and how they fail. I got a little bit of